and directly proceed to Andrzej's talk. Looking forward to hearing about a double copy at genus 1 from twisted cohomology. Please go ahead, Andrzej.
First, I'd like to thank the organizers for giving me the opportunity to speak at this wonderful conference. So I'm going to present something that came out last December with 2 students at Brown and another one at Uppsala University. Both of these guys are now postdocs at Leipzig and Queen Mary. So, yeah, why is the double copy interesting? Well, it basically says that gravity is gauge theory squared, and gravity is very hard, and gauge theory is in some sense easy, so we're getting something hard by squaring something easy. So the first instance of this comes from KLT in '86, where they showed this genus 0 for genus 0 amplitudes in string theory, and since then the one loop string theory double copy has been sort of difficult, and there's been a lot of recent developments on this, but there's still a few pieces missing. And I want to contrast this to the field theory double copy, in which we now have tons of, dozens of double copies out there, and we've gone to very high loops, to like, 5 or 6 loops. And so we have a new mathematical tool that's come into play in the last 5 years in amplitudes called twisted cohomology. It appears in Feynman integrals, string integrals, cosmological correlators. So the idea is to see if this can tell us or help us with this genus 1 double copy problem in string theory. So the plan is to just review the genus 0 story, then go very quickly through the genus 1, and then give some conclusion. So everybody in this room is probably familiar with a picture like this, where we have some sort of sphere integral with some marked points as a bilinear in disk integrals. And so the amazing thing is that this sphere integral, the integrand is just the square of this disk integral. And so in some sense, squaring the integral, we actually is essentially the same as squaring the integrand is the same as squaring the integral up to these very important KLT, these very important functions coming from the KLT kernel, and that's essentially what we're interested in today. What are these guys in green at genus 1? So I want to start by looking at the anatomy of the open string integral on the sphere. So we've got some integration cycle. This is just tells us the ordering of the marked points on the disk. We've got some holomorphic differential form, just some Park-Taylor, and we've got this universal multi-valued function called the Koval-Nielsen. So we're going to call this the twist, and it has a very important property that it has multiplicative monogeries. So this is exactly what twisted cohomology is designed to study, integrands with multiplicative monogeries. So I want to view this integral as a pairing between a twisted cycle and a twisted cocycle. So the twisted cocycles, they're just differential forms, except when I construct the cohomology, I construct it with respect to this covariant derivative due to the presence of this multi-valued function called the twist. So it just needs to be covariantly closed and not covariantly exact. This is the same thing for the homology. I get some modified boundary operator, but it's a little bit more complicated, so I haven't written it out here. But in essence, the twisted cycle is a topological cycle tensor, a branch choice for how to evaluate the twist along that cycle in the integrand. And because of just by properties of this twisted boundary operator, this topological cycle is allowed to end wherever the twist vanishes. So in this case, whenever the punctures collide, so Zi equals Zj. Okay, so we're all very familiar with this pairing of integration where I take a cycle and a cocycle and get a period. But actually it turns out that when you construct these twisted cohomologies, you get a dual cohomology, a dual homology automatically, and there's more pairings. Not just integration, but in this horizontal direction, which we call intersection numbers. And these intersection numbers are an inner product on the vector space of cohomology and homology, respectively. The cohomology intersection number, you just take some sort of dual cocycle and you wedge it against a regular cocycle, you integrate over the whole manifold. There's some regularization that you have to do, but it's not important. Sorry, I forgot to tell you that this dual space is exactly like the regular space, except you have to take our twist U to U dual, which is just the inverse of the twist. It's the same as changing alpha prime to minus alpha prime. Okay, and so the homology intersection number is, we get this topological intersection number, so it's just plus minus 1 depending on the orientation that these cycles intersect. And then there's this extra factor where I get this product UU dual evaluated at this intersection point. And it's very important that this is, this product is single valued. So it's just some sort of complex number or phase. And so now that we have all of these spaces and we know how to pair them in various different ways, it turns out that they satisfy this very nice relation called the twisted Riemann bilinear relations. And it basically just says that my cohomology intersection matrix is equal to a matrix product of my period matrices and this intersection matrix of homology. So this one's actually sort of shocking because this intersection matrix is actually a rational function of Mandelstamm's and alpha prime, and I'm getting some rational function from taking a matrix product of transcendental functions and some linear combination of phases from this H matrix. It already sort of looks suspiciously like a KLT formula, except, C shouldn't be rational, to be something complicated, some transcendental function. And this is not an accident, because when I chose that my U dual should have been inverse U, I didn't actually have to make that choice. I could have made a different choice. I just need to make sure that U times U dual needs to be single valued. So I could choose U dual to be U bar instead. And then I can just take the same formula on the last slide and take all my little dual check symbols and turn them into bars. And then the Riemann twisted bilinear relations is on the nose the genus 0 double copy. So we get the cohomology intersection number just becomes the closed string integral. What was the dual period matrix becomes the complex conjugate of our open string amplitudes. And then, okay, the period matrix stays the same for this guy, it's just the open string. And then this guy, this homology intersection matrix, is the KLT kernel. And it actually doesn't change from the previous slide to this side. And so there's nothing really stopping us from trying to generalize this formula to higher genus, like mathematically. So that's exactly what we want to do. So after chiral splitting, the one-loop string integrals look something like this. We've got a twist or a Koebel-Nielsen factor that's multi-valued. So at genus 1, we have to use these theta functions, and inside of them we put the difference zj minus zk. We also have this new factor, E, which is x of some dot product between L and K, which I've called SIA, and our function. And so these theta functions, what the important property for us is that they're quasi-periodic, so that they have some non-trivial B-cycle monogamy. And the full string integral, it's too challenging. We don't really know how to classify the full twisted cohomology for that. So instead, we want to look at a simpler problem, which has been studied by mathematicians before. And these are called Riemann-Wittinger integrals, and they are essentially just if I integrate only over one puncture in the string integral. And so what these are explicitly, we have some twist U, which is just the Z1 part of the Koebel-Nielsen, and then we put one of these Kronecker-Eisenstein functions that we saw in Ollie's talk, multiplied by the holomorphic differential for our differential form. So, yeah, the only important part of these Kronecker-Eisenstein functions for this talk is that they are also quasi-periodic. They have some non-trivial multiplicative monogamy from a B-cycle. So if I combine the entire integrand together, the twist plus these Kronecker-Eisenstein functions, I also find that I get multiplicative monogamies over the A and the B cycle. However, I have to sort of define that that I keep this combination of Mandelstamm's, tau, the punctures, and this extra bookkeeping variable from eta from Ollie's talk constant. So this is some mathematical constraint that's needed for all of this to make sense. And then, of course, we have the sort of normal monodromies around whenever Z1 goes around some other puncture Zj. Okay, so now I can tell you what a basis of cohomology and homology is for these Riemann-Wittinger integrals. A basis for cohomology, you just take these f functions, multiply them by a holomorphic derivative, and inside the argument I can take Z1 minus any of the other punctures. And then for homology, well, my cycles have to, I have to end on the sort of stretch between two punctures. So I can have this, I fix the first puncture, Z2, to be at the origin, and then I can have an A cycle, a B cycle, or I can have any cycle stretching from Z2 to any of these other points. I could conversely choose these green cycles instead. So if I chose, and in particular, this is actually a nice choice, if I assign the blue to the regular homology, and the green to the dual homology, you'd get some nice diagonal intersection matrix. But it doesn't matter. You can make any choice. So in particular, for the simplest example that I can really write on a slide, I've just chosen to use the same homology basis for both dual and non-dual cycles. And so very explicitly here, we have some analog of a closed string integral, but for these Riemann-Wittinger, we've got f bar, Kobold-Nielsen squared, or twist squared. And this is indeed some matrix product with some KLT kernel that I compute using the intersection numbers in homology. And then these are just our periods and our complex conjugate of our periods, so our open string analogs. And so we did a bunch of numerical checks for this. So for example, if I take the same differential form, so let's say I've got this phi 3, whatever that is, but if I just take phi 3 and wedge it against phi 3 bar, the integrand is manifestly real, so if I integrate over this, I should get something real, right? And so I wanted to show you all the different pieces that go into this double copy formula. They all have, for the most part, imaginary parts and complicated that you know. And somehow all of this mixed together in exactly the precise way that I do indeed get something that's real. And furthermore, if I can look at these sort of off-diagonal double copies where I take phi 3 bar and take phi 2, and it turns out that this double copy formula provides an analytic continuation in comparison to the direct integration, because eventually the direct integration no longer converges anymore, but this double copy formula keeps working. And as you can see, they definitely agree to a very high precision. Okay, so that's it. We wanted to demonstrate that twisted cohomology gives us a good way, or at least some sort of way of trying to tackle this higher genus double copy problem. We can just take these Riemann bilinear relations and use them. And in the future, you know, we'd like to, get rid of that sort of. I didn't write it on. Sorry, I started saying something I didn't write on my slide. We'd like to get rid of this this condition here, where we keep this constant. We also need to learn how to include the loop momentum, so consider differential forms not only on the torus, but also have DL components. Even just restricting to the torus, including multiple integrations over multiple punctures. It's not quite fully understood how to set that problem up in the language of twisted cohomology. But interestingly, everything should generalize very straightforwardly to higher genus if we restrict to one-dimensional integrals. And yeah, that's it. Thank you.
Yeah, thanks a lot for this inviting invitation to double copy country. Let's start with questions to Andrzej. So you spoke of non-commuting monodromies. What about using non-commuting variables, like a non-commuting version of Ada?
Yeah, I mean, that's one idea that's floating around, but we haven't played with it enough say anything concrete about it.
And have you explored much the implications of your integral relation upon expanding in eta alpha prime or combinations thereof?
Just to first order, essentially. Yeah, what do we find? We find, yeah, it looks very much what you'd expect from a string integrally driven Bettinger at first order, but then they start to deviate at higher orders in alpha prime and get sort of messy due to this constraint. This constraint right here. But the first order looks roughly what you'd expect.
Further questions? Okay, then let's thank Andrzej again.